Hello everyone, I'm Zhiyang. Today my topic is DeepCon contribution current testing for deep learning systems. As well known that deep learning has achieved great success in various applications in the last decades. It is increasingly adopted in safety critical systems such as self-driving car, medical diagnosis, and malware detection. This correctness and security of these DL-based systems are critical, and unreliable DL systems can lead to fatal crashes. For example, as shown in this slide, the unimpacted driving condition in the deep learning-based self-driving car caused a fatal crash. Thus, DL-based systems need to be systematically and thoroughly tested. Traditional deep learning testing treats the testing activity as a black box, that is, divides the majority of the dataset into the training set and divides the majority into the testing set. This makes it difficult to qualify the thoroughness of DNA testing. To facilitate the measurements of the test adequacy of DNAs, we need some current criteria to qualify our testing. However, traditional software testing techniques do not apply to DNAs. This is because the DNA decision logic is embedded in the neural connection weights and the layers, not in code. We thus need to construct a new carrier criterion for DNAs, new carrier matrix for DNAs. Inspired by said carrier in traditional software testing, DeepCon proposes a neural carrier criteria to measure how many unique neurons have been activated by test input. For example, if we only consider the output value greater, if we only consider the neuron whose output value greater than 0.2 as activated, the neural carrier over this 3-4 layer fully connected DNA is 62.5%. DeepCon inspires a group of studies such as DeepGauge and DeepCover. DeepGauge proposes a group of K-multi granularity neural coverage, in which the output of a neuron is partitioned into K sections. DeepGauge measures how many unique sections have been covered by test inputs. DeepCover proposes an MCDC carrier criterion based on the condition decision dependencies between adjacent neurons. However, existing neural output-based carrier criteria can also be limited. As well known during the predicting process, the outputs of neurons and the connection weights that emit together determine the final prediction results. But existing neural output-based carrier criteria only consider the output of neurons and ignore the connection weights that emitted by these neurons. This will lead to some misfitting. For example, as shown in the left part of the slide, if we only consider the output of neurons, then the neuron N10 that outputs 0.4 will be more important than the neuron N11 that outputs 0.2. However, since the connection weights emitted by these two neurons are different, the contribution from N10 to the predictions neuron N20 is obviously greater than that of N11, and the importance of N11 should be greater than N12. To this above mentioned end, we propose DeepCon, which includes a novel contribution carrier standard that can truly cover neurons and the connection weights that emitted at the same time, and a test case generation approach, DeepCon generation, guided by the carrier criteria. Let let us first look at the proposed contribution covering criterion. To fully cover both the outputs of neurons and the connection with the emit, we first introduce a term contribution to present the internal logical coverage of DNA. We first define the contribution from previous neurons N1 to N2 as the product of the output value of N1 and the connecting W12 that emit from N1 to N2. Besides defining contribution, we also need to define contribution activation. We define contribution activation as follows. For a given input X and a threshold T, if the normalized contribution is greater than T, it is said that the contribution is activated by X. Here, the normalized function is computed according to this formula. And the capital letter UNX represents contribution from previous neurons to neuron N. The reason why we normalize the contributions is that the value range of the contributions in different capital letters UNX may vary larger. For example, as shown in the bottom of this slide, the range U1, U2, U3, and the range U4, U5, U6 are different. Now, let's look at an example of contribution activation with threshold T 0.25. The normalized contribution UN10 equal to 0. Thus, the contribution is not activated, and the other two contributions are activated due to the normalized contribution are both greater than 0.25. After defining the contribution activation, we need to extract the activated contributions of different inputs. We thus propose backpropagation contribution extraction, as the animation in this slide shows. It extracts the activated contributions back from the output layer until the input layer. Now, we can give the definition of contribution coverage, that is the number of activated contributions divided by the number of the total contributions in the DNA. For example, in this slide, the number of the contribution activated by X is 8, and the number of total contributions of this DNA is 15. Thus, the contribution coverage is about 53%. After calculating the contribution coverage covered by the test set, the last question is that how to activate those contributions that have never been activated. We thus develop DeepCon generation, a contribution-guided test generation for randomly select inactivated contributions U12. If we can make both the contribution U12 and the output of neuron 2 larger, it is possible that contributions U12 can be activated. Thus, we transform the test generation into a joint optimization problem, in which we construct a joint objective function. This objective function is constructed by selecting U12x and N2x. For scalability, DeepCon generation uses a gradient ascent-based method to iteratively optimize the joint optimization so that the input seed X mutates towards the direction that can activate the inactivated contributions U12. Note that the gradient over U12 and N2x with derivative 2x are different. This may lead to joint objective function optimized towards one of them and ignore the other. To overcome this problem, we adopt a penalty strategy, that is, add a soft Hanger loss. and make sure U12X and N2X can be activated at the same time, especially if a part in joint objective function is activated. We ignore the following changes of X towards the direction of this part. This strategy can make the joint objective function be optimized towards the direction of the other part and make it be activated quickly. Last, we show our experiments results. The evaluation subject is shown in the top half of this slide. We select 3 classical lineage models on mixed dataset and 2 bigger DNA models, VJJ19 and Resonate 15 on ImageNet. We evaluate DeepCon and DeepCon generation by investigating 3 research questions. That is, question 1: how strong is the coverage of DeepCon? Can it scale well to larger DNAs? Question 2: compared with the existing works, how good does DeepCon perform in terms of coverage strength and what's the real example detection? And question 3: how efficient can DeepCon generation active inactive contributions and find unimpacted behaviors of DNAs? About the research question 1, let us first look at the experimental results as shown in these slides. Under the settings of t larger than 0, the contribution coverage of any of these DNAs grows with the increase of test inputs and does not research 100% even on all test inputs, and a larger t will result in a lower contribution coverage. And as the value of t becomes larger, the corresponding contribution coverage drops much faster. Moreover, contribution coverage criteria can scale well to larger DNAs, such as VJJ19 and Resonate 15. About the research question 2, since the activated contribution extraction method in DeepCon is completely different from neural output-based coverage criteria, the contribution defined in DeepCon is the combination of a neuron and the connection with it connects to the next level neuron. Thus, the neural coverage in DeepExplore may be a potential object for fair comparison. For the perspective of coverage strength, since one neural corresponds to multiple contributions, the coverage strength or contribution coverage criterion is stronger than that of neural coverage. From the perspective of usefulness in adversarial example detection, we also performed a compare of our DeepCon with neural output-based coverage criteria. The idea of this detection is that normal inputs from the same category tend to cover some of the same neurons, while adversarial examples tend to cover different neurons. We use DeepCon and neural output-based coverage criteria to extract active logical units and calculate the similarity between normal examples and adversarial examples respectively. The experimental results show that, on average, the AUC of DeepCon exceeds that neural output-based coverage criteria by 13%. About the research question 3, based on previous experiments, we try to activate the remaining inactivated contributions of all models. As shown in this slide, on average, DeepCon generation can efficiently activate 93.63% of the remaining inactivated contributions, and while neural coverage fails to expose any defections of DNAs, about 62.6% of the generated tests of DeepCon generation can lead to the mispredictions of DNAs. The high proportion of adversarial examples in the generated example indicates that contribution coverage has higher potential usefulness in exposed DNA defections. Thank you for your listening. Is there any question?